Okay, today we're going to do a couple new things. We've already been solving log equations, but we're going to do applications and we're going to do graphing today. So basically we're going to have some real world problems that involve logs, and we're going to do some graphing, basically teach you the parent function and that kind of stuff. All right, let's start with a solving one like you should already be pretty good at. Now this one, I know you might be tempted to start by subtracting 5 and then dividing by 6, but that's not a good idea. Because this part right here can be simplified to a simple number. 3, you are correct. How can that whole box turn into a 3? Because the 125 can change into a 5 to the third, and therefore the answer is 3. That means you can put a 3 in right here. Go ahead and solve it from there. Turn it my way and I'll tell you if you're right or not. Now you realize you started downloading later than everybody else, so it's going to take longer too. I get the math on that. I'm sure you do too. Yes, nice job, nice job. Yup. Yup. Divide those again and you'll get a different answer for that. There you go. Yup. 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 Let's do it one more time. Yup. What'd you get? Yup. Yup. All right, I'm almost with everybody at this point, and you end up getting it down to 30 equals 5x. And so then x must equal 6. Okay. Now, did we ever do a square root on both sides? No. If we had, and we had to come out with two answers like plus and minus whatever, usually, but not always, usually you have an extraneous answer. Let's say that had happened in this problem, and we had to come out with plus 6 and minus 6. It's not an automatic, listen, it's not an automatic that the negative is extraneous. Look at this problem. If you put in a negative 6, does it cause this problem to crash? No. If there was a number, an x there, it would cause it to crash. If there was an x there, you couldn't have a negative. It would cause it to crash. But just because there's a negative over here, that doesn't cause it to crash. All right, so some of you guys really did not get the extraneous thing on the last test, the quiz that we took. Take a look at this one. What's the first step? Can you do that little thing where you just solve this and get a number, like find out that that's going to be like 6? No, you can't. Why not? Because there's an x down in there. So you can't do it that way. So how do you do this one? Divide by 2. Everybody start by dividing by 2, and then try to do a rewrite. Get the log out of there by doing a rewrite. Something to something equals something. Now, I don't have a problem with you eating that, but either eat it or don't eat it. Don't keep on picking it up and making him want it and all that stuff. All right, so here we go. That's 6x to the negative 4 equals 16. That's the most common mistake. What did I do wrong? What am I missing that's making this wrong? Parentheses. Because, see, a lot of people think, oh, so I'll just divide by 6 next. Wrong. You can't do that. Because there's parentheses around this. Because there's little imaginary parentheses around that. There always is. And so when you put it to a power, here's the way I think of it. Why should it only be the x that's put to the negative 4th? Okay, this is your last chance to stop turning and talking to people, otherwise you're going to be moved right there. Too much sugar this morning, now you're eating more. All right, so this x is put to the negative 4th, but so is the 6. I mean, couldn't you write 6x as x times 6? Isn't that the same exact thing? And then if I had moved it, it'd have been like this. X times 6, and now the 6 is being put to the negative 4th. Should it just be random, like what number happens to be there? ends up being put to the negative fourth? No, they both have to be put to the negative fourth. So the best way to do it is to remember that you have an x, or sorry, a parentheses right there. Okay, so now I put it to the power of negative 1/4. That's something you can do in your head. Because the fourth root of 16 is 2, and the negative makes it what? Flip. So not just 2, it's 1/2. And this one becomes 6x equals 1/2. And now to get rid of the 6, yes, I could divide by 6, but it'd be, oh, question? Good question. We do have that absolute value thing, but let me, okay, but since the negative might end up being a problem if we put a negative there. Would you agree? In fact, it will be a problem if we put a negative there. So I'm going to skip that absolute value thing, even though you're right. Technically, what I should do is go absolute value of 6x equals this, and I'll get a negative answer, but I know the negative answer is going to get canned anyways in this problem. So I'm going to divide by 6, which is smarter actually to multiply by 1/6 times by 1/6, and I get x equals 1/12. Raise your hand if you had that one right. Okay, now, kids that also put negative 1/12 on the test, I get that you were being extra smart in that you were realizing that we did a fourth root. But then the problem is, and this kind of a problem, if you put a negative in right there, you've got a negative base, and that's not allowed. So you should have crossed off your negative answer and said it was extraneous. My dream answer for a kid would be 12, and x equals negative 1/12, and I cross it off and say extraneous. That means you knew enough to know that there was a fourth root, but you also knew enough to know that the negative 1 couldn't work in that problem. Yes? Yes, they are graded, and you'll get them back later. This is a good chance to talk about common mistakes before you look at it. Maybe you'll look at it and go, oh, crap, I did that thing you talked about. Turn to the yellow sheet, the third problem. All right, first thing I do is a rewrite. And then you might realize, wait a minute, I've got to make common bases. Okay, if you get this far, hopefully you remember that the only way you're going to solve this kind of problem is if you can make these two bases be the same. And then the exponents will be equal. All right? So what should those two bases be? Should you bring them down to like 3/2, or should you leave them as 9/4? Can you make this other one work with a 9/4? You actually can. You can leave it as 9/4. So then this guy needs to be changed into 9/4. Give that one a try. See if you can change that 9/4. It's 9/4 to the something. Now I got to bring this part down. This is still to the 1 power. Now, I can't just do it this way because this is not equal to this. So I got to make them equal. So 9/4 to the what? 9/4 to the negative so that it'll flip. And then I got to square both of them. Raise your hand if you knew it was -2. All right, good. Then I've got a common base, and then those multiplied equals that. So -2 times -x makes 2x equals 1, x equals 1/2. Now, if you had to be sure, absolutely positive that your answer was right, you could take it and stick it back in. Stick in the half right here. The question is, does that really work? Well, at least it doesn't cause it to crash. We didn't make the base negative, and we didn't make the argument negative, so that's okay. At least we got that going for us. But then we'd have to do this one would be pretty complicated to try to check. I guess we could go 16/81 to the power of -1/2 should equal 9/4. So the 1/2 power means square root. That'd be 4/9. And then negative makes it flip, 9/4. Yay, it worked. I know it's right now. So take advantage of that. These are kind of problems where you can know if you're right or not. If you just go back and check it and see if it works, you know if you did it right. Yes? Yep. Yes, you absolutely could. So like right up in here, the question was, could you have made them both have a base of 16/81ths? And this one would already be fine, 16/81ths, and to the negative x. And then this one we could change 9/4 into 16/81ths to the power of something. The power of -2. Okay, let me make sure that I've done everything right here. Okay. So then 9/4, I'd need to make that. No. It's not -2 power. Here's what. Do you get what we just did is substitute this for that? Are you saying that if you square 16 and you square 81, they're going to equal 9/4? Ah, see, that's not a -2. That'd be a negative what? 1/2. And now you have -x is equal to -1/2, so x equals 1/2. So, yeah, you could do it that way, but it was a little trickier. Had to be careful on this exponent right here. But it works just fine, yes. You can use any base you want. As long as you can change both of them into that base, it's good. All right, go on to this one. You see how steep this beach is? One might assume that it was like a storm that made the beach this steep, but it wasn't. There is a reason why some beaches are really steep and some are not. So if you want to use Google Earth for a minute, we can see where this beach is. If you go to Playa de Cocos, sorry, I'm not a Spanish speaker. Playa de Cocos, did I say it right now? Okay, go ahead, give it a shot and see where it is. I'm going to pause for a second while I do. Okay, I'm recording again. So here we are at Del Coco Beach in Costa Rica. And if we want to zoom in on that beach, of course, from this perspective, the beach is going to look flat. But you're looking at pictures? It's all a matter of which angle you take the picture at. I can tell you, I have been to steep beaches, and I'm going to tell you why they're steep in a minute, but there are some beaches that are incredibly steep and some that are always incredibly flat. And there's a reason. It's not just a storm went through. Can you think for a minute, what could it be about sorry, not a deep. Yes, of course, it has to do with logs. Oh, some of you cheated already. Don't even talk then if you went and cheated and looked already. What is it about the beach? The equation is about logs, of course, but the question is, what is it about the beach that makes it steep? Yes? That is an excellent guess, and it's about like how the depth off the shore. That's a really good guess. But that's not it. But at least I know you didn't cheat and look at the next page. No, I'm not saying you did. I'm just asking that you not look at the next page. Okay. So, all right. So here's the problem. That's the problem with posting notes that that you get to see the next page. I guess I will get to it. I've been to beaches that are really flat, and I've been to beaches that are really steep. The really steep ones have really big pebbles of sand. Like the little grains of sand are super big, like they're little, like really small rocks. Okay, as opposed to super fine sand. Like how many of you been to Fort Myers Beach? Raise your hand if you've been to Fort Myers Beach. That's only 4 of you. I thought there'd be more. That is a super flat beach. You won't be able to see it from Google Earth. So let's get out of Google Earth and instead go to just use a Google search and type in Fort Myers Beach. Look for some pictures of Fort Myers Beach. If you see people walking on it, you're going to see it is incredibly flat. Have those of you that have been to Fort Myers Beach, do you remember the type of sand it had? Super fine sand, like powder. It's like so powdery that it's really hard to get off of you. Do you know what I'm talking about? If you've ever been to a beach where the sand is super fine, where it's like You can't even scrape it off yourself because it's like teeny tiny little particles. Okay, that kind of sand makes a really flat beach. So if you've seen any pictures of people walking on Fort Myers Beach, you'll see that that beach is like so flat. In fact, it's so flat that it's a really popular business to rent bikes to ride on the beach. You wouldn't be doing that if the beach is sideways, like, you know, like at a 45-degree angle. Nobody would want to ride on the beach. All right, so the other place I was that had super steep beaches, like this beach that we see on the screen, was in Hawaii. And the sand in Hawaii is oftentimes really big grains of sand. Now you can have one side of an island have really big grains of sand and therefore steep beaches, and you can have the other side of the island be super fine sand and therefore be very flat beaches. So it doesn't have to be on, you know, one island can have only one kind of beach. You can have one beach right next to another beach where the grains of sand are big and therefore it's very steep, and where the grains of sand are very small and therefore very flat. All right, let's move on. So the slope S of a beach is related to the average diameter in millimeters of sand particles on the beach by this formula. This is a typical problem. We're going to give you a formula, and notice it's got a log in it. Now on this one you will need to use a calculator. So everybody grab your graphing calculator. Find the slope of the beach if the average diameter of the sand is 0.25. Well, this is such a classic math problem. They've given you a formula. They've given you a number to stick into the formula. The only thing you really have to figure out is where to put the number that they gave you. So 0.25 millimeters is the diameter of the sand, and that should go under either S or D. You look up in the directions and say, the slope is S, so it better not be that. The diameter is D, so that must be where it goes. And you stick this number in there, and now how would you do a calculator for this? I would probably go, do you have to type in base 10 on your calculator? Does it know that it should use base 10 when you hit the log button? Yeah, if you hit the log button, it assumes base 10. So, when it says log base 10 of 0.25, all you'd have to do is type log 0.25. Then you times that by something else, then you add something else, and then you'll have your answer, and then turn it my way and tell me what you think it is. Zoom in on it so I can read your answer. If you have a negative answer, that's a sign that something might be wrong. You're finding the slope of the beach. Okay. Oh, I get what you're saying. But how about this? I'm not saying that slopes can't be negative. I agree with that sentiment. The slopes can be negative. But did we do anything that should cause a negative answer? Isn't that a positive? Oh, it is a negative? What is log 0.25? Just what is log 0.25? Help me with that. Okay. So now you'd multiply that by this, which makes it a lot smaller, and then you'd add that. So I'm still thinking that it probably would come out positive. Turn it my way so that I can see what your answers are. I am seeing one answer that's more common than another, but it isn't like everybody's getting the same thing. So, all right, 0.0879 is the answer, which of course depends on how you round it. Where, you know, if you round to the tenths place or hundredths place or thousandths place. We typically use 3, and therefore 0.088 is probably a pretty good choice. All right. I think you know that if we stuck this number in, we'd put it in the other spot, right? So you'd put it over here, and you just have to solve. How do you solve when you have a log in that spot? I want you to try it right now. Everybody take this 0.5, put it here. You're going to get rid of this by subtracting 0.159 from both sides. And then you're going to divide by this. And let's see if you know how to do it at the very end. So here's what I'm getting. I'm getting 2.889 equals log base 10, but I don't even have to write that, D. Okay. Now, can I rewrite this thing? Yeah, but now I will need that base. 10 to the power of 2.889 equals D. Now keep in mind how big these are. I know that that's a big number, but 10 to the power of 2.889. But that's not in inches. That's not in feet.
That's like millimeters. That's still huge. Not really. That's like this big.
774. 7 centimeters. You move the decimal over 2 spots, right, to get from centimeter or from millimeters into centimeters. Okay, wait. Is this in millimeters? Let me check. It's in millimeters. Okay, so 774 millimeters. And when you move for decimals in from millimeters to centimeters is 1 spot, wouldn't it be? So it'd be 77 centimeters. Small boulders, right? Now let's think about though, what does the slope of a half look like? That's a really steep beach, isn't it? Think about a beach that's like that. Okay? That is a beach. Yeah, that's not really a beach even anymore. It's like that. It's pretty much like a cliff. Have you ever seen cliffs? Are they sandy at the bottom, or are they big rocks? Huh? All right, so basically if you have boulders, when you have boulders, they're naturally not going to be flat. Have you ever seen a boulder beach that's all flats? I haven't. All right, so the point is, this is kind of an extreme example. We probably should have used numbers that are a little bit smaller because the slope of 0.5 is throwing it off. We really should have had a slope that was like 0.025 or something really flat, because most beaches are pretty flat, aren't they? You don't see beaches that are at a 45-degree angle. It's not a beach. All right. Anyway, let's move on. This is another application question, and I thought it was interesting. It's about decibels. I went and found this one on the internet. This is the formula for getting decibels, and a whisper is supposed to be this. I looked that up. A whisper has an intensity of 5.4 times 10 to the negative 10th. That's a very small decimal. And that's measured in watts per square meter. Well, bottom line is, I got 2 variables again. I got D, which is decibels, and I got I, which is intensity. And which should I give you, D or I? I gave you the I, and I want you to figure out the decibels. So you're going to put this in there. Use the calculator. Now this is going to fool some people because they don't understand how to use their calculator well. But if you know how to type in scientific notation and use your parentheses right, it's very doable. Once you figure out this weird decimal, you're just going to take log of it and times by 10. The last parts are easy. Get what I'm saying? Just got to find the weird decimal in the box and take log of it and times it by 10. And tell me what you get. I know what this answer is, so I'll be able to tell you if you're doing it right or not. Yeah, since it's log base 10, you don't even really need this 10, because when you put it in a calculator, you won't need that 10. But you do need this 10, because you need to divide your I by that. Turn it my way. You are correct, 27 decibels. Now, you might be saying, what? That seems way too high for a whisper. I understand. But I double-checked this thing, and decibels are really weird. I've got a stereo system that gives how loud something is in decibels, and it's like kind of inverse of what you would think. Did you get 27.3 approximately? All right, good. You already did. If you got 27, you did it right. All right, and I know 27 seems like too big of a number, but double checked, and everything is correct if you got 27. Let's move on to the graphing part. So let's talk about graphs. So you need to know what the parent generally looks like. Have I told you yet my little thing about logs and how they're like trees that have blown over? All right. Would you agree that a log is basically a tree that has fallen over, they've cut it down or whatever, and now that's what makes it a log versus a tree. You don't walk into the forest and say, oh, look at all the logs, right? But when there's logs, they have already been cut down and they're on the ground. So just go with me. This is a tree. This is like a tree. And this tree, yes, you have to cut down trees in math class today. It's starting to fall over, right? And in fact, it won't be a log until it's actually blown over. And so here is this is like the tree part, you know. That is what logs look like. That is a graph of a log. Yes. See, here's the roots in the ground, down in there. Okay, but anyway, that's your parent graph of a log. Now, exactly what points does it go through? Only one nice one and a lot of weird decimals. It depends on which one you're doing. This one, we're asking you to graph log base 3 of 3. Sorry, log base 3 of x. So I'm going to write that bigger. Log base 3 of x. So how do we know exactly what points it goes through? Well, you pick some points and you stick them in. What's a common thing to put in for x? 1. Good. Do you remember if you won the argument, what do you get? Nothing. 1 for x and 0 then for the total. Okay, what's another thing I can put in? Yes, but log base 3 of 2 is not fun. Log base 3 of 3 is fun, because that's easy to do in your head, so let's put in a 3. Log base 3 of 3 is what? 1. If these two are the same, the answer is the exponent, which is a 1. Okay, and I have one more tip for you. 9 is a good choice, because it's the base squared. You get what I mean? If I put in a 9 here, that happens to be 3 squared. A base squared works out nicely. So I'm putting in a 9, and I would get 3 squared there. And then if there's a 3 squared here, the answer is 2. Those are 3 points that are on my graph. Now, there's one more point I want to point out that because sometimes one of these points will go off your graph too far. And this next point I'm going to show you always is on the graph. It's if you make this number right here, the x, into the 1 over the base. Does anybody see why that would be smart? It isn't equal 1, no. Because do you get that this 1/3 is really 3 to the negative 1? You got how that works? Why is that good? Because now these are the same, and therefore the answer is negative 1. So if I put in a 1/3, I put in a 1/3, I get a negative 1. That might go over some of your heads, and that's okay. All you really have to do is find me at least 2 points. Sometimes the third point is not on the graph. If you find me 2 points in the asymptote line, I'm going to be fine. All right, so 1, 0 is right there. Another one's 3, 1, 1, 2, 3, 1. See, I made my log wasn't quite blown over quite far enough. See what I mean? Because I got to go through that point. And then 9, 2, that'd be like here. So I was making mine not quite steep enough. So bottom line is the red graph is much better than the black one. The black one is just a quick sketch. The red one is an actual real graph because it's going through some points. One last thought, there is an asymptote that's running right here, meaning it will never go cross through that line. It'll never touch 0. The asymptote line is right on the y-axis, and therefore it's x equals 0. So don't forget about that asymptote line too. All right, move on to this one. This one's the same exact thing, except it's been moved. So do you remember where we just were? We were just here, and then it was 3, 1, and it was 9, 2. Put those points on there again. Now where do we need to move? The parent function, including the asymptote line, which I'm going to draw in with this neato thingy. There. I have to move that graph somewhere. Well, if I just look at what's happened to the parent function, what does that mean, do you think? Come on. Left 4, very good. Remember those? Remember when we did y equals x squared and then we'd like change it to x minus 2 and that may move to the right 2, that kind of stuff? All right, so it's just like that. What does plus 4 in by the x mean? It means left 4. So I got to take all these points and move them left 4. And then there's that 2 in the front, which means I got to stretch it up and make it twice as tall. Doesn't this sound like a real pain to have to move it all the way over and then stretch all the points? Yeah, it does. So if it were me, I would think about how that's going to look. I know generally it's going to go over here. And I generally, when I stretch things, it's like you grab a hold of it and it stretches up like this. I know generally it's going to look something like that. But exactly where? That's where the XY chart is your friend. You can take the XY chart and like fill it out for this. Now, this takes some serious math ability. You have to think through and say, I want to make that 1, because if you won the argument, you get nothing. I want to make that 3, because then the base and the other base will both be 3. And I want to make it 3 squared, which would be 9. Or I could make it negative. Sorry, I could make it 1/3 also, but that's kind of a tricky one. So let's do one thing at a time. How can I make this equal 1? Because if you won the argument, you get nothing. If you put in a -3, excellent. Put in a -3 there, you get how you'd get 1. And if there's a 1 right there, the whole rest of it here is going to all multiply by 0. So you get 0. So -3 comma 0 is on the graph. All right, next up. Looks like I moved my graph a little too far. See, I can already make an adjustment on my graph and say, I should have not quite moved it quite that far. So there, I made a little adjustment. Okay, now I'm going to try another point. And by the way, when I move that, do you get I need to move the asymptote? Otherwise, I'm going right through the asymptote, and that doesn't make any sense. The asymptote needs to move to the left 4 spots also. All right, now another point I can make this. If I could make this be a 3, it would be really good. How can I make the thing in the circle be a 3? If I made x -1. Go on making that a 3 is a good thing? Because then the 3 is a base, and then this is going to be 3 also, which makes this whole thing equal 1, but don't forget the 2 out front. And the whole thing isn't 1, it's 1 times the 2. 2 times 1 makes 2. -1 comma 2. Look at this. -1 comma 2. Oh, my red one was actually pretty close. My black one was off a little bit. So it really, I'll take this black one out of here. That was a good guess, but now I'm getting real numbers here. I'm going to get one more important point. What if I could make this thing into a 9 in here? To make that a 9, do you get I need to make x be 5? Because then it's 5 plus 4 makes 9. Why is 9 good? Because then if there's a 3 here and this is a 9, which makes a 3 squared, then the answer is 2. And then you don't forget to multiply by the 2 in the front, would make 4. So 5 comma 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. There. Here's my new graph. It's been moved and stretched. Okay. All I really need you to know is 2 things. What does the parent look like? And it looks like a tree that's been blown over. Number 2 is use an XY chart so that you can find out exactly where this thing moves. Because it's kind of hard to move your graph perfectly left 4. That's not that bad. But the timesing it by 2, making all the heights twice as high as they were, that's kind of a pain. So if this XY chart is too hard for you, you can do it that way. You can take the parent points, move them 4 to the left, and then make them go twice as high as whatever they are. That'll work if you like that way better. And in the end, the answer would have to be like this, going through at least 2 points and having the asymptote line. Now the third point on this one is going to have gone off my screen, I believe. So that's another reason why not a bad idea to only require you to have 2 points. As long as those 2 points and the asymptote are all in good spots, you'll probably be fine. All right, moving on. This one, just compared to the parent, log base 7. Let's get some parent points on here for log base 7. If you've won the argument, put a 1 right there. What do you get? 0. If I put in a 7 right here, if I make it the same as the base, what's the answer then? Come on, what's log base 7 of 7? Say it. 1. Okay. And then what if I make this, wait a minute, if I'm going to make that 49, it's going way off my graph, isn't it? That's why it's probably a good idea to just have 2 points for a requirement. Could you also put in 1/7 right there? Some of you that are really on to this stuff, yeah, that would be smart, because that'd be 7 to the negative first power. And if you put in 1/7, you would get, this really becomes 7 to the negative 1, which makes the answer -1. But you don't have to have that point. I understand that would be a pretty tough, tricky one. So where is 1, 0? It's right there. Notice that they always seem to go through that. 7, 1, 1, 2, 3, 4, 5, 6, 7, 1's right there. So this one's a tree that's been way blown over. The bigger the base is, the sharper the turn it makes. See, this one's a base 7. The other one we were doing was a base 3. The bigger the base is, the flatter they are. Okay. Then, if you were going to have to do this one, it's just the same exact thing except flipped and moved. That's not right 3. What's that? Where's it been moved? Down 3. Good. So I take my graph, I move it down 3. 1, 2, 3. And then I do a up-down flip or a left-right flip. What's this one? Left, right, or up-down? Is it horizontal on the inside or is it vertical on the outside? Hi-vo. Is that negative on the inside or the outside? That's on the outside. There's no parentheses, and therefore it must be on the outside. So that negative is on the outside, and it's vertical on the outside, so it's a vertical flip. This is kind of tough for some kids to see in their head, but it basically looks like that. That's an up-down flip. Everything goes up here. If you want to, you can do it 1 point at a time. So this point reflects up to here. That point reflects basically there. This point right here would go about 2.5, so that's about there. This one is about there, so I was off a smidge, but okay. That's a reflect up down. Enough learning for today. It's kind of a long day. So your assignment is posted. It's nothing super incredibly hard, but this is the day after the quiz, and so you've got to move on to new stuff, and it's kind of harder than average day, I understand. All right, that's all I got for the video for today.